In the next few videos, we're going to take a look at the trigonometric functions. And over here, we've got two of our trigonometric functions, sine and cosine. These are two functions that we have already graphed in previous videos. If you refer back to a few videos ago, you will find that we looked at the sine theta and cos theta graphs, and we looked at a single period of those graphs from 0 to 2 pi, or from 0 to 360 degrees. And we saw that in red, this is what we had for the sine theta graph, and in blue, this is what we get for the cosine theta graph. In the next few videos, we're going to explore the sine and cosine graphs in more detail, and we're also going to take a look at the tangent graph. That is something that we haven't seen before. So we're going to look at the tan graph, and we're going to see how our sine and cosine graphs can vary when they're not in these most simple forms. The general form of a sine function, for example, is f of x is equal to a sine theta plus q. And thus far, we've dealt with examples in which we had an a of 1 and we didn't have any q. That is just our sine theta graph, what we have in red here. So in this lesson, we're going to take a look at what will happen to this graph with different values of a and different values of q. And the same goes for the cosine function. The standard form of a cosine function is going to be f of x is equal to a cosine theta plus q. And in the next video, we'll take a look at how our cosine function is going to change as we change our a values and our q values. But for now, let's take a look at the sine theta graph in more detail. So over here in red, we have our sine theta graph, and we're going to be starting out here at 0 degrees and ending at 360 degrees, or if you're dealing in radians, 2 pi. And that is the period of our sine graph. And if this is unfamiliar to you, I suggest you refer back a few videos ago where we looked at the sine and cosine curves in more detail. So this is going to be the standard sine graph. We're going to start out at 0 degrees with sine theta having a value of 0. Over here, when we are at 90 degrees, or pi over 2 in radians, we're going to have our sine graph reaching its maximum value of 1. Over here, when we're at 180 degrees, or pi if we're dealing in radians, we're going to have our sine theta value again reaching 0. And over here, which is 3 pi over 2 in radians, or 270 degrees, this is where we're going to have our sine graph reaching its minimum value of -1. And here at 360 degrees, or 2 pi radians, we're going to again have our value of sine theta at 0. And that is the standard sine theta graph. Now, I mentioned at the beginning of this video that the standard form of a sine function is f of x is equal to a sine theta plus q. And we can see that this curve in red is going to be the graph that we get when we have an a value of 1 and a q value of 0. That is just sine theta. So now let's take a look at how this graph is going to change based on differing values of a and differing values of q. Let's start out with q. Our q value is going to represent our vertical shift. And what that means is that if we have a q value greater than 0, our curve is going to shift upwards. And if we have a q value less than 0, our graph is going to shift downwards. And this is not unfamiliar to us. This is the same trend that we saw when we were dealing with exponential and hyperbolic functions. We found that q was often representative of our vertical shift, and this is no different. Our value of q is going to shift this curve upwards or downwards on this plane, depending on what our value of q is. So our q is our vertical shift. What about our a value? Our a value is going to affect the amplitude of our graph. And if you're wondering what the amplitude is, this maximum here is known as the crest of a wave. So this point here is the crest of our wave. It's the highest point of our wave. This point here is the trough. This is the minimum point of our wave. So when we're talking about the amplitude, we're talking about this distance, either the distance from our baseline to our crest, or we're talking about the distance from baseline to our trough. When we're dealing with a wave, the distance from our baseline to our crest is going to be the same value as the distance from our baseline to our trough. So either of these is going to be our amplitude. That is the amplitude. If our A value is greater than 1, we are going to increase our amplitude. If our A value is between 0 and 1, in other words, our A value is a fraction, then we're going to decrease our amplitude. So in this case, we have an A value greater than 1. Our amplitude is going to increase, which means that this graph is going to be stretched vertically. It's no longer going to have maximums and minimums of 1 and -1. We're going to be stretching our curve, so it's going to have greater maximums and smaller minimums. If our A value is in between 0 and 1, that means that our A value is a fraction. We're going to decrease our amplitude. That means that our minimums and maximums are no longer going to be 1 and -1. They're going to be less than that. So our curve is going to be smaller. It's going to be less stretched than our red curve. Now, there's another very important thing that we need to look at when we're dealing with our effect of A. Depending on whether A is positive or negative, we're going to have a curve that either looks like this or one that looks like a reflection of this if our A value is negative. If we have a positive A value, we're going to have a graph that looks like this. This is going to be the shape of our graph if we have a positive A value. If we have a negative A value, our graph is going to look like this. It's going to be a reflection of this graph about our axis here. So let's say, for example, we had an A value of -5. Now, when we are dealing with negative A values, if we have a value that is going to be less than -1, so if A is less than -1, we are again going to have an increase in our amplitude. We're going to have an increase in our amplitude, however, our curve is going to look like this. We're going to have a reflection because we have a negative A. If we have an A value that's in between -1 and 0, that means we have a fraction but a negative fraction. We are going to have a decrease in our amplitude. But because this is going to be negative, it's going to be a reflection of our graph. So it's going to look like this instead of like this. So the takeaway from this is basically that if we have a whole number for our value of A, whether that number is positive or negative, we are going to increase our amplitude. So this graph is going to be stretched more. And if that is a positive number, it's going to look like this. And if it's a negative number, it's going to have a reflection over here. So it's going to look like this. If we have a fraction for our value of A, we are going to have a decrease in our amplitude. So it's going to be stretched smaller. And depending on whether that fraction is positive or negative, our curve is either going to look like this or it's going to look like this. Now, you might be asked to determine the Y-intercept when you're dealing with these trig functions. And when you're trying to find your Y-intercept, that is going to be this point right here. It is going to be the point at 0 degrees. And at 0 degrees, sine theta, when theta is 0, is going to be 0, which is going to make this entire term 0. So our y-intercept is going to be equal to q. So let's make a note of that right here. Our y-intercept is equal to q. So in the case of sine theta, when q is 0, our y-intercept is 0. Here we have a value of 0. But if we had, let's say, a Q value of 1, we know that we're going to have a vertical shift upwards, and our new y-intercept is going to become 1. So I'm going to finish off there for this video, and in the next video we're going to take everything we've learned in this lesson and apply it to an example and see if we can make things a lot more clear.